So the first thing we want to do is find the first and second derivative of the given function, and I've done that here already. And over here on the right side, because the TI does not have like cotangent and cosecant, you have to input it in its cosine and sine forms. So I just rewrote the cotangent as cosine over sine, and I rewrote the cosecant as 1 over sine on the first derivative, and then for the second derivative I had to rewrite the cosecant as 1 over sine, and then the cotangent also as cosine over sine. So what we want to do is, I said produce the graphs of f, so we're going to have to graph these in the graphing calculator. So we would just put those into our graphing calculator just as they were on that piece, on that last page. From here, it asks us to find the intervals of increase and decrease. That's the first thing. So if we were to be working this out by hand, to find the intervals of increase and decrease, we'd have to first find the first derivative and then determine when the first derivative is equal to 0 or undefined, and those would be our critical numbers. And then you kind of set up your number line and determine if the first derivative was positive or negative when you break up the number line using those critical numbers. But since it asks us to use the graph here, it's actually a little bit easier to use the graph. So what I'm going to do here is, I have all of these graphs now. It's kind of jumbled, so I'm going to go back and I'm just going to turn off the original graph and the second derivative. So I just want to have a look at the first derivative. It's the red one. So when I graph this, it should just have the first derivative by itself. So when we're finding intervals of increase and decrease of a function, we can look at its first derivative's graph, and anytime the first derivative is negative or below the x-axis, then the interval is decreasing. It's a decreasing interval. And anytime it's positive or above the x-axis, then that's an interval of increase. So what we need to do is find these critical numbers here graphically. So we can use this using the graphing calculator. There's a function to find these zeros on the calculator. So if you press second and calc, you have the second option, which is 0. It'll find the zeros of a graph. So it's going to ask you for a left boundary and a right boundary. So if I want to find this first one, I want to scroll over using the arrow. You have to click it a few times until you see the X. And it's asking you to put in a left boundary to the left of the 0 that you're trying to find. So I'm to the left of it now. So then I press enter. Then it says right boundary. So now go to the right of that 0. Scroll over. So now I'm to the right of it. And I press enter. And that's asking me, do you want the calculator to make a guess at the 0 here? So we hit guess, and then we get negative 1.297. We can round that to a negative 1.30. So we can go write that on the other page. So our critical number, our first one is negative 1.30. Then we can go to the next one. Same thing, second calc. So now we go 0 again, so that's the second one. Now we want to find this one here. So now I'm going to scroll. The left boundary will be to the left of that 0. So now I'm slightly to the left of it. Enter. Now it's asking for a right boundary, so move to the right of it. Enter. And it says that one is negative 0.58. And for the sake of time, I'm just going to write the other ones out. Um, this graph is symmetric, so this one's going to be positive 0.58 and this one's going to be 1.30. But also, the thing we have to remember for critical numbers is that it's not just where the first derivative is 0, it's also where it's undefined. So you can see we have a vertical asymptote here, so it's not defined here. And then also, we have to recall that the domain of the original function was restricted between negative pi and pi. So we have a 1 over sign for this cosecant. So pi is going to be undefined also. So we also have 3 more critical numbers at negative pi, 0, and pi because they're vertical asymptotes there. So I'm going to write those out too. Actually, negative pi would be further to the left. I want to kind of keep them in order, so we're going to squeeze this in here. Negative pi, and then positive pi. So those would be our intervals. If we were doing this by hand, we set up our number line and we test values between negative pi and negative 1.3, and then values between negative 1.3 and negative 0.58. Oh, I need to stick the 0 in here too. Forgot about that one. And intervals here, we just test values between each of these. But because this one asks us to use the graph, it's actually a lot easier to see. And what we have here is anything below the x-axis is going to be an interval of decrease because it's negative. The slope would be negative, and anything above would be an interval of increase, and that's because the slope is positive. So we know these values are negative 1.30, negative 0.58, and we have a 0.58 and then 1.30. So we can conclude that the intervals of increase are only from the place where we saw the positive value. So it was between negative 1.30 and negative 0.58, and then we can union that with the set 0.58 to 1.30. And the intervals of decrease would be all of the other intervals, because everything else, as you can see on the graph, is below the x-axis, so it's negative. So from this negative pi to negative 1.3, and then from negative 0.58 to 0, 0 to 0.58, and then 1.3 to pi. Those are all intervals of decrease. So next they want the inflection points of the function. So if you go back to the graph, the We find inflection points when the second derivative is uh, equal to 0 or undefined. So if we were doing it by hand, we'd find the second derivative, set it equal to 0, and then determine when that second derivative function is 0 or undefined. Once again, with the graph, it's also slightly easier. So let me go in here and let's pull up the second derivative graph. So we turn off the first derivative, and then let's look at the second derivative. So to determine where the second derivative is equal to 0, we do the same thing finding the zeros of this graph. We just see where it crosses this x-axis. So we want to do second, calculate, then we want to find the 0 here, so it's the second one. So we have to scroll our cursor. Sometimes it's down, it starts like close to this axis, so if you want to move to the on this piece of the graph, you just move it left. Left boundary, right boundary, enter, and then give it a guess. And it says that's negative 0.86. So that's a possible point of inflection. So now I'm going to do the right side also. So second, calc, second one is 2. So now we want to move to the right side. So we'll just move to the right until that cursor ends up over there. So it's the same number, just opposite signs. So our possible points of inflection are negative 0.86 and positive 0.86. So to find the actual points of inflection, we take those and we substitute them into the original equation. So this is what we're looking for our points of inflection. So we want to find f of negative 0.86. Now this is the original function. And then we want to find f of 0.86. The good thing is we put the original function in the calculator, so we can find this pretty easily using our graphing calculator. So let me get out of the graph. Remember, we put the original function into the first slot, y1. So there's actually a way we can get it to evaluate the function pretty easily for us. So if you press vars, scroll over to yvars, and then choose the first option, function, it's going to give you a list of all the different functions that are on that list of graphs. So choose the first one because that's where I put the original function. All you have to do is put the input in with the parentheses, so it's kind of like function notation. The calculator is going to evaluate whatever we have in this first function at the value that we put right here. So that is negative 3.89. So as an ordered pair, that would be negative 0.86 and comma 3.89. Negative. for the sake of time, it's the same value here, but you do it the same way. So it would be positive 0.86 and 3.89. And finally, for when the function is concave up versus concave down, it's very similar to the intervals of increase and decrease, except we're using the second derivative this time instead of the first derivative. So we know it's concave up when the second derivative is positive, and it's concave down when the second derivative is negative. So if we go back to the graph, this is the graph of the second derivative. This second derivative is positive because it's above the x-axis from negative pi, which was our vertical asymptote, to this value was negative 0.86, and then it's also positive here. This other vertical asymptote was 0 to 0.86, and then we know it's concave down whenever the second derivative is negative or below the x-axis. So that would be from negative 0.86 to 0 and 0.86 to pi. So let's write that out. We should be done.